Hello guys, from this video I am planning to uh, explain a series of videos involving calculus part. So these are the lessons involved in calculus. You can see it. There are 11 lessons in the total 11th and 12th. A total of 11 lessons are involved in calculus part. We shall discuss these all lessons one by one in detail by a series of videos. So let us start our video with the first lesson of calculus, functions. So now let us discuss what is functions and what is the definition of function. It is I think somewhat most important is the definition of the function. So let us get into it. First of all, let us discuss the definition of function. What is function? Function is a relation between two sets pertaining to some conditions. Some conditions are applied. Function is a relation between two sets. Let we represent the two sets by two Venn diagrams. Let those be A and B. So these are some elements in set A and these are some elements in set B, right? So what is a function? Function is a relation between two sets such that there is some condition. The first condition is that every element in the set A, the first set, every element in the first set should be mapped, should be related. First of all, what is a relation? Relation is some algebraic expression involving these two sets. So that relation should be a function if and only if they satisfy these two conditions. The first condition is every element in the set 1 should be mapped to A. The second condition is every element in the first set should be mapped. That is the first condition. What is the second condition is the image should be unique. Every element should be mapped to a unique element in B. By combining these two statements, what I can tell is every element in the set 1 should be mapped to a unique element in set 2. That's what the function is. If every element in the set 1 is mapped to a unique element in set 2, then such a relation is function. Every element should be mapped and the mapping should be unique. Every element should be mapped to a unique element in B. So this is what some Venn diagram approach. Coming to graphical approach, let us go with the graph to determine whether the relation is a function or not. These are same. Coming to graph, there will be no sets. The two sets will be x-axis and y-axis, right? So every element in the set 1, that means every element every point on x-axis should be mapped to a unique element in set B. Means here it is y-axis, right? So combining this all statement, one thing I want to tell, that means every x should have a unique y. That's what, by graphical approach, that's what the function is. Every x should have a unique y. Let us see. Let us go with graphical approach. This is the origin, y-axis, y dash x dash x, right? So if we consider some function, like let us consider this relation. Is it a function? If we see for this particular x, that is, let us name it as x1, we are having two y's, that is y1 and y2. This particular x1 is not having a unique y, so this particular relation what we have drawn we represented with some graph is not a function. We can tell simply as, when we draw a line parallel to y-axis, if it cuts the graph at a single point, then it is a function, or else it is not. Simply, if we draw a line parallel to y-axis, if it cuts the graph at one point, any line drawn parallel to y-axis cutting the graph at a single point, then that relation is a function. I can tell this by graphical approach as simply as any line drawn parallel to y-axis should cut the graph at single point. So it is cutting at 2 points, so certainly, definitely, the relation by which this graph is drawn is certainly not a function. Not a function, right? So by this I can tell one method. Relation f from set x to y is a function if I will provide a statement. Let us consider two elements x1 comma x2 such that they belongs to the set x. So let us claim x1 equal to x2, and if we are able to prove, f of x1 equal to f of x2 by considering x1 equal to x2, if we are able to prove f of x1 equal to f of x2 by considering x1 equal to x2 such that x1 comma x2 belongs to x, then definitely the function, the relation f is a function. And definitely the relation f is a function. Let us understand this. Why? If we understand these two conditions, and if we are able to understand the graphical approach, then this y is I think it's simple. Just analyze this method. Why it is like this. If x1 equal to x2, then f of x1 equal to f of x2 implies that the relation has unique image in the set 2. You can analyze it. I will leave it to you. Why? If x1 equal to x2, then f of x1 equal to f of x2, then such a relation is definitely a function. Why? Just analyze these two statements. It will be clear. So this is what function is defined. So next, let us get into some terms in function. What is the domain of a function? What is domain of a function? What is range? What is codomain? These are some terms involved in defining a function. When a function is given, every function will have a domain, range, and codomain. So let us understand these terms so that we'll be in a great clarity, right? Because these are some small terms, but domain, range, and I think this total whole lesson functions is useful, and this is the origin of everything. A circle is a function, a parabola is a function, a hyperbola is a function, and everything logarithms is a logarithmic function, exponential function. So everything is a function. So the basic function, the topic function, the definition of the function, I think somewhat pretty important. So let us get into it. What is domain? Domain is the set of values of the set 1. I mean, we are going the functions with set 1 or set 2 or x-axis and y-axis. So I will go with x and y. So set of values of x where the function is defined is known as domain. Domain is the set of values where the function is defined. In the domain set, the function is defined. The function itself is defined in the domain. So domain is the set of values by which function is defined. I think this is input. This is input to a function. I think this is set 1. These are all inputs given by a function f. So this is the output. These are the outputs what we get. So domain is input, range is output. Range is set of output values. I can say range as set of output values. What is codomain? There are two sets. What I said initially, what I said is function is a relation between two sets, right? So the first set is domain and second set is codomain. So the function itself is defined if every element in the first set is mapped. So every element in the first set is mapped. So every element in the first set is defined for function. So first set itself should be a domain. First set itself should be a domain, and second set is codomain. And but every element in the second set need not be an image, but every element in the first set should be mapped, but it need not be mapped to every element in the set 2. So set 2 is codomain, but it may not be a range. But set 1 itself is a domain. So I think set 1 is everywhere. Set 1 is domain and set 2 is codomain. And what range is that? The set of values by the set of images of A is range. Simply the set of output values is range, and the set 2 is codomain. The set 1 itself is domain. That's it. And so now let us try to discuss about some functions and try to get their domain, range, and try to analyze those functions. So firstly, exponential function. Exponential function is defined as f of x equal to a power x such that a not equal to 1 and a greater than 0. This is what exponential function is. So let us try to get this domain of this function. What is the domain? F of x equal to a power x. So what are the set of values of x such that f of x is defined means set of values of x such that a power x is defined. A power x is defined for every value of x, so I think the domain is R. So now let us try to get what is its range. I think if you can see, a is greater than 0 and x is any real number. By taking a greater than 0 with the exponent can be any real number, I think the result will be always be positive. The result should always be positive. I think you can get it. For every value of a greater than 0, if we take x be any, if we take negative, let a be 2, let it be minus 3, it will be 1 by 2 power 3, 1 by 8, right? So no problem. I think let it be any number x, the range will be R plus set of positive real numbers. You know, it is set of real numbers. So we are done with the exponential function. So let us get into logarithmic function. What is logarithmic function, right? The logarithmic function is defined as f of x equal to log x to the base a such that x greater than 0, a greater than 0, not equal to 1. This is what logarithmic function is. This is the inverse of exponential function. We can see it in detail. I mean, what is log? Such that if we name f of x as y, log x to the base a, such that a power y equal to x. This is what log is. If the operation is such that y equal to log x to the base a, if and only if a power y is x. So now let us try to get the domain of the logarithmic function. What is the domain? Domain is in the definition itself. It is defined as x greater than 0. So I think domain is set of real numbers. What is range? Let it be any number greater than 0. Here x is always greater than 0. Then is there any restriction to y such that x greater than 0? Y can be any number to get a positive x. So I think y can be any real number. So y is nothing but f of x. F of x is nothing but the output. So the set of output values is nothing but set of real numbers. So the domain of logarithmic function is set of positive real numbers, and range is set of all real numbers. And coming back to, let us get into, we're done with the logarithmic function, and the next one is signum function. What is signum function? Let us get in detail. What is signum function? Signum function is defined as f of x equal to 1 for all x greater than 0, 0 for x equal to 0, minus 1 for x less than 0. Signum function is defined in such a way. So for every value of x it is defined. So simply the domain is set of real numbers. What is the range? For every value of x we are getting -1, 0, 1, that's it. So the range is set of -1, 0, 1. This is what the range is. So this is what the story of signum function, right? So coming to the next one, what is it? Modulus function. What is modulus function? Modulus function is defined as f of x equal to x for all x greater than or equal to 0 and minus x for all x less than 0. This is how modulus function is defined. It is denoted by f of x equal to mod x, and here also it is f of x is a signum function, then it is defined as sgn of x, right? So let us try to find the domain of modulus function. What is the domain? For every positive numbers including 0, here it is defined, and for every negative numbers also it is defined. So I think set of all real numbers is its domain, and let us find the range of this function. What is the range? Let us try to draw the graph of this function. For every x greater than, so for every x, let us first name it. It is y-axis, it is dash x, and it is origin, right? For every x greater than or equal to 0, f of x equal to x, then it is y equal to x. It is like this, right? And for every x less than 0, it is f of x equal to minus x. The graph would be like this, but it is only for x less than 0, so it's like this. So the set of output values are all positive. By taking any number on x-axis, the result is always positive. The result is always positive. So the range is set of all positive real numbers, right? So this is how we can find the domain and range of the functions, right? There are some more functions to discuss, and we can analyze it. We can find the domain, range, and we can know the graphs, and we can see, but for now, as of now, we shall skip that part, and let us get into some types of functions. If we get time, then we would be discussing some trigonometric functions and try to find the range, domain, and all. But as of now, let us skip that part and jump into types of functions. The first one is what is 1-1 function? What is 1-1 function? A function is said to be 1-1 if we shall go to the Venn diagram and sets approach. So when we are defining a function, we are telling that every element in the set 1 is uniquely mapped to an element in set 2. The element to which it is mapped is known as image, and in the set 2, the element in the set 2, the this element is known as image of this element, and this one is known as the pre-image of this particular one element. So now let it be x and y, let it be x and y. Y is the image of x and x is the pre-image of y. So while discussing one functions and one and there is another one known as onto, we should discuss we should introduce the term pre-image so that we shall get the concept in clarity. There will be so many problems asking whether it is a one or onto, or it is there are some two types of functions. So there will be options, and such questions are pretty frequent. So let us understand the scenario, what's happening and what is the definition and what's the criteria to a function to become a one function, right? So let us discuss in detail. So let us consider two functions a and b, two sets a and b. Then a function is defined from set a to b. So that particular function is one if and only if every element in b have a unique pre-image in a, right? Unique pre-image in a. Let it be so many functions, so many elements in set b, and these are so many elements in set a, right? So if it is one if and only if being a function, if it is one function, then definitely it should be a function. So the two conditions of the function should be satisfied. Additionally, every element in the set B should have a unique pre-image in A. Generally, let us go to functions. In functions, there is a restriction that if it is x1, x2, x3, if it is y1, y2, y3, then this element should be uniquely mapped, right? But there is no restriction that this is a function, and mapping x3 to someone, some y3, it is definitely a function, because here y1 is having two pre-images. It is not having a unique pre-image, but x1 and x2 are having a unique images. What is the definition of function is that every element in set 1 should have a unique image in set 2. If it is 1, if I ask is it a 1 function, then definitely not, because additionally the definition of 1 function, every element in set 2 should have a unique pre-image in set 1. So it is not a 1 function. So in order to satisfy the criteria of 1 function, the three conditions are: every element in the set 1 should be mapped uniquely to a image in set B. That means every element in set 1 have a unique image, and every element in the set 2 should have a unique pre-image. That's what the function 1 function is. Now let us try to understand. Let us define as f of x equal to x square, right? Let us try to draw the graph of this function. This is y dash, x dash, x, and this is the origin, right? So it is a parabola, like this or like this, right? So now considering, if we take for -1 it is 1, and for +1 it is also 1, right? So how I tell to whether it is a function or not? Firstly, it should be a function. It should be a function. To become a 1 function, firstly it should be a function, right? So firstly let us see if it is a function or not. Let's try to draw any line parallel to y-axis, then it is cutting exactly at one point. If we see any line drawn parallel to y-axis, cutting the graph at only one point, so it is definitely a function. So now the next question is it 1 or not? So in order to try, or in order to check whether it is 1 function or not, we have to go with the definition. What is the definition? Is that for every element in set 2, it's not every element, sorry, the element to which it is mapped should have a unique preimage. So firstly, what is set 2, right? What is set 2 is that y-axis. Those are the output values, those are codomain. So for this particular value 1 on y-axis, we are having two preimages, -1 and 1. So this is definitely not a 1 function. 1 function is that unique preimage, but not to every element in set 2, but the element which is mapped in set 2 should have a unique preimage in set 1. So that is what the 1 function is. By graphical approach, I can tell that any line drawn parallel to x-axis should cut the graph at only one point, then definitely the function is 1 function. So if we have to go with the graphical approach to check whether a relation is a 1 function or not, first we have to check whether it is a function. So we have to draw a line parallel to y-axis and check whether it is cutting the graph at exactly one point or not, and then we have to go with a line parallel to x-axis and then check whether the line is cutting only at one point or not. So this is the kind of method we have to adopt when we go by graphical approach to check whether a function is 1 function or not. There are many problems involving giving a function and whether it is, there will be 4 options, 1 onto, into, or many one, like that. So this is what we can find. And another method I would suggest is that if we consider f from x to y is a 1 function, we can tell it is a 1 function if we take x1 comma x2 belonging to x, and if we claim as f of x1 equal to f of x2, and we are able to prove x1 equal to x2, then definitely this particular function f is a 1 function. Similar way, when what we did in functions, in the definition of function, here also we can try by checking whether it is a 1 function or not, because f of x1 equal to f of x2 means two elements in set 2 are equal, then definitely those two should be from a same one. That is what these two statements are suggesting. You can analyze it. So this is one of the method when going to by graphical approach. We can tell that a line drawn parallel to x-axis, then if it is cutting at only single point, then it is one function by one algebraic method. It is some algebraic method. No, the origin is definition, unique preimage. This is what one function is, right? So what is the conditions? Condition to be 1 So A is a set and B is a set. The condition for 1 is cardinal number of A should be less than or equal to cardinal number of B, right? I think you got it. Every element, if every element is mapped, then definitely every element should have a preimage. So if this condition is satisfied, if and only if this condition is satisfied, then only the element in B has a preimage and the given relation is also a function and it should be 1. Then combining these two conditions, it should be satisfied to a function becoming a 1 function. For a function becoming a 1 function, n of A should be less than or equal to n of B, right? So that is what. So now let us try to find how many 1 functions can be defined from n of A, from a set A to set B is n of BP n of A, where npr equal to n factorial by n minus r factorial. So we shall discuss this proof later, so that we can save some time. And another one more point, number of functions, this is number of 1 functions defined from A to B, and what is the number of functions defined from A to B? That is n of B power n of A. N of B power n of A is the total number of functions. Total number of functions defined from A to B. We shall discuss these proofs in permutations and when we get into the chapter permutations and combinations in detail. You can get this proof in detail. Up to then you should accept it, right? So going to what is onto function. Coming to onto function, simply speaking, the range should be codomain, right? When I am saying about function, there are two sets, as I told. The point is that every element in the set B should have a preimage. Onto function is also a function. In addition to that, every element in the set B should have a preimage in set A. That's what. If every element in the set B has a preimage, the element which is having preimage will be considered as under the element of a range. So if every element has a preimage, then every element should be element of a range. So every element is if every element is a element of a range, so then range should definitely equal to codomain. That is what B, right? So if codomain equal to range, then the function is onto function, and the condition for onto function is n of A greater than or equal to n of B. And if n of A equal to m and n of B equal to n, the number of onto functions defined from n set A to set B is n power m minus nc1 n minus 1 whole power m plus nc2 n minus 2 whole power m, so on, to where it ends up to 0, where ncr equal to n factorial by n minus r factorial into r factorial, right? This is what onto function is. So let us going to next one, that is what is a many one function. Many one function is just simply the converse, or the function which is not 1 1 is simply a many one function, and into function, the function which is not onto is simply a into function, right? So from this we are end up with the types of functions under some on the basis of some classification, and coming to another some more types of functions. It is what is an even function. What is an even function? A function is said to be even function if a function f is said to be even function if f of minus x equal to f of x for all x belongs to domain of that function, right? For all x belongs to domain of that function, we are domain. So if f of x equal to f of minus x, if we draw the graph, for every x and minus x, for every x and minus x, we will have same images, like we will have same output. So definitely the function should be symmetric about y-axis, right? If for this particular x1, suppose it is the value is suppose it's y1, right? So definitely for minus x1 also it should be minus y, it should be y1. So these two will be under the graph. If suppose if it is for 0, if it is 0 and some x2, if it is y2, then definitely for minus x2 also it should be y2, such that it will be symmetric about y-axis. So every even function is symmetric about y-axis, right? So this is what. And one more point, y-axis means the equation of y-axis is x equal to 0. One more point I would like to tell is, if f of a minus x equal to f of a plus x, then definitely the function f is symmetric. Then f is symmetric about x equal to a, about the line x equal to a. This is some important point to be noted. So this is what even function is. So coming to odd function. Function f is said to be odd function if f of minus x equal to minus f of x for all x belongs to, again, the domain of the function. Right. So similarly, by drawing the graph and taking an example, we can know that every odd function is symmetric about origin, or we can say it as symmetric in opposite quadrants. opposite quadrants. You can check it by taking an example, or you can generally prove it, or and then accept it. Another important point is that I would like to tell, or I would like to mention, is every function f of x can be written as the sum of even and odd function, right? Plus f of x or minus f of minus x by 2. So f of x can be written as like this, right? If we solve this, we will get f of x, right? So since LHS equal to RHS, this equation is valid. If we check, it will be this particular term, this particular one will be even function. You can replace x by minus x and check whether we are getting the same one or not. And this particular one is odd function. This is one particular point I would like to mention. We can use it somewhere, it will be useful somewhere. So yeah, this is one of the important point. And another type of function I would like to mention is a periodic function. What is periodic function? A function f of x is said to be periodic if for some t f of x plus t equal to f of x, then f of x is a periodic function and t is called as a period of the particular function. And then what is the fundamental period is the least value of t such that f of x plus t equal to f of x is known as fundamental period of that particular function. The least value of t for which f of x plus t equal to f of x, the least value. If t is a period, then if p is a period, then np is also a period, where n is an integer. We can know so in detail about the periodic function in trigonometry. Else let us see one example, right? F of x equal to cos x, right? Let us try it. Draw the graph of the graph cos x. Cos 0 is 1. Something like this. It will be minus 1, 1. It will be something like this. It's 0. Pi by 2. It's pi. It's 3 pi by 2. Something plus pi by 2. It is 2 pi. And something like this, right? We take 1 and 1 is coming for 0, it is 1, and 1 is coming again at 2 pi. So f of 0 equal to f of 0 plus 2 pi for f of x equal to cos x, right? So here by taking, if we replace 0 by x and check it, it is true. F of x equal to f of x plus 2 pi for all f of x equal to cos x. So 2 pi is the period of f of x equal to cos x. So this is what periodic function is. We've already discussed about one function and onto function. Now let us discuss one more type of function is that is one onto function, or it is also known as bisective function, right? I forgot to mention one thing. Onto function is now also known as surjective function or surjection. One function is also known as injective function or injection. So this is bisection. So what is bisection? The function which satisfies both the conditions of one function and onto function is known as one onto function or a bisection. So what are the conditions? Conditions are same, and we have discussed about the cardinal number. When discussing about cardinal number in one function, we have discussed in this way, and in onto function we will discuss in this way, right? So combining these two function to become a bisection, n of a should be equal to n of b, and if n of a equal to n of b, number of onto functions is defined as n of bp n of a. When n of b equal to n of a, it will be n of a factorial or n of b factorial. Number of bisections defined from a to b. What is the reason for discussing bisection here is that next I want to discuss about what is inverse of a function, right? What is inverse of a function? Inverse of a function is defined if the function, firstly the function should be bisective to become a to get an inverse. To have an inverse, the function should be bisective. So how to find the inverse of a function? First step is that firstly we should let f of x equal to y, then x equal to f inverse y, and we should try to get x from the given equation. Let us see one example. F of x equal to 5x plus 3. This is one problem. Let us try to find the inverse of this particular function. First, let f of x equal to y, then y equal to 5x plus 3, then x equal to y minus 3 by 5. By this step, x equal to f inverse y, so we can write this one as f inverse y equal to y minus 3 by 5. If f inverse y equal to y minus 3 by 5, replacing x with y with x, f inverse x equal to x minus 3 by 5. Simple. Considering f of x equal to y, writing x equal to f inverse y, and try to get subject as x and try to get x in terms of y. That's it. That's how to calculate inverse of the function. And there is one particular lesson of like inverse trigonometric functions, so there we get the importance of what the inverse of a function is. So that's it for functions. That's all for functions lecture. Functions is the basic. I think it's the basic of total calculus. So try to analyze the concepts and get the concepts clear. I think every concept is clear in this lecture, and one thing I want to tell is understand the one function and onto functions, the scenario, and what's the exact definitions of one and onto functions in detail, because there will be more there are plenty of questions involving asking whether the function is one or onto, or it's bisection or not. So try to understand, and questions on how to find the domain. I think domain is set of values by which the function is defined, right? So what is defined? When any expression is undefined, some cases are there where any expression becomes undefined when there is denominator becomes 0 or a square root of a negative number. So these are some basics we have to catch in order to find domain. So this all lesson is the basic and it is the first step of calculus. So we have to understand in detail. We have to get the basics in detail and we have to get the clarity on basics so as to excel in further calculus. So if you like the video, do like, share and subscribe. Thank you. Another type of function is a composite function. Composite function involves three sets. It will be set A, set B and set D. A function f defined from A to B, that a function g defined from B to C, then a composition is defined B to C, then a function from A to C is defined, which is known as composition of f and g. It is G circle f. G circle f is defined as a function from A to C. If f is a function from A to B and g is a function from B to C, then a function from A to C is defined known as G circle f, which is known as composition of G and f. G circle f of x is defined as G of f of x. Similarly, we can do composition of two same functions. Like we can do f circle of f of x. It is known as circle. So f of x. This is one kind of function known as composition of function, is known as composite function, right?